Welcome, friend, to this quiet corner we've carved out together. Take a soft, gentle breath with me now. Where are you in this moment? What time is it for you? Perhaps the world outside is bustling, or maybe it's already hushed, settling into the deep, tranquil hours. No matter where you are, or what thoughts might be swirling, know that here, there's no need to rush, no answers to chase, no expectations to meet. This is simply a space for your mind to wander, to float freely among the grandest concepts the universe holds, like whispers in the cosmic night. Let curiosity be your soft blanket, and wonder your gentle guide as we drift through the magnificent mysteries of existence, simply for the peace of the journey. This isn't about learning or seeking medical advice. It's about finding a quiet comfort in the vastness. Allow your mind to drift gently now, like a tiny leaf upon a tranquil river, unhurried, unburdened. We will journey together through one of the deepest mysteries of the cosmos, a concept that might leave you feeling both awestruck and, in a curious way, profoundly at peace. We speak of black holes. Perhaps you have heard tales of them before, these invisible giants that devour light itself. But have you ever truly paused, perhaps closed your eyes for a moment, and tried to envision what they truly are, not through dramatic images or dry numbers, but through a deeper, more profound sensation of the very nature of space and time? Imagine space, not as an empty void that we simply move through, but as a vast, soft, infinitely stretchable fabric. A fabric that can bend, that can ripple, that can undulate like the surface of a calm lake when a small pebble is dropped upon it. For ordinary objects, like a planet or a star, they create a gentle dimple, a slight depression on this cosmic fabric of space. This, in essence, is how we perceive gravity, not as an invisible pull, but as the natural tendency to move along the curves that mass itself has created. It is much like a marble rolling across a stretched rubber sheet with a bowling ball in its center. The marble will naturally curve inwards towards the heavy object, but with a black hole, the story takes an entirely different, almost unfathomable turn. Picture an immense concentration of mass, compressed to an unbelievable degree, placed upon that very same fabric of space. The dimple is no longer a gentle curve. It becomes an infinitely deep well, a bottomless funnel, where the fabric of space is stretched and pulled to the point of tearing, creating a region where all familiar laws of physics seem to dissolve, to cease their gentle, predictable hum. This, at its very core, is the essence of a black hole. It is not a solid object in the way we understand matter, but rather the profound, almost incomprehensible result of the extreme warping of space-time itself. And because of this extraordinary warping, some truly peculiar things begin to unfold around them, things so strange, so deeply unsettling to our conventional understanding, that they can fundamentally alter your perspective on the way the universe operates around you. Some of these phenomena are so profoundly bizarre that you might struggle to believe them, were it not for the robust mathematical foundations that underpin their existence and properties, and the steadily mounting observational evidence in our own universe that these intricate mathematical predictions hold true. Take a gentle breath in now, and slowly release it. We are in no rush. Let your mind open softly, receiving these concepts like drops of night dew, shimmering and full of quiet mystery. Black holes, you see, come in an astonishing variety of sizes. At the smaller end of the spectrum, we have observed black holes that are only around 3.8 times the mass of our own sun. These are the celestial newborns, the quieter members of this cosmic family. On the other side of the scale, we find black holes that have existed for almost the entire age of the universe. titans weighing billions of solar masses. These behemoths are not only incredibly massive, but also so immense in their physical scale that they could comfortably encompass our entire solar system within the diameter of their event horizon, the point of no return we will soon explore. Imagine our Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all nestled serenely within the confines of such a cosmic leviathan. The black holes being created in the universe today are typically the final, dramatic stage in the life cycles of particularly massive stars. When such a star is born, it is, in essence, a grand cosmic balancing act, held precariously between the might of two opposing forces. The first force, constantly pushing inward, is gravity. It tirelessly pulls every speck of the star's enormous mass towards its very center, a relentless squeeze that seeks to collapse everything into the densest possible configuration. But deep within the fiery heart of the star, a counterforce is born. In the crushing depths, hydrogen atoms, the most fundamental building blocks of the star, are pressed and fused against other hydrogen atoms with an astonishing intensity. This profound pressure and heat initiate a process of celestial alchemy. They combine to form a denser element, helium. This new atomic structure, helium, remarkably, requires less energy to hold its form than the two individual hydrogen atoms did. And so, the surplus energy, the magnificent excess, is released. This unleashed energy constitutes the second force in our star's delicate balance. It radiates powerfully outward from the star's core, in the form of searing heat and brilliant light, directly counteracting the immense inward press of gravity. In this beautiful, dynamic, and fragile state of equilibrium, the star will remain relatively stable for vast stretches of cosmic time, sometimes for millions, even billions of years. It burns brightly, a consistent beacon, a cosmic furnace churning out warmth and illumination, providing the steady outward pressure that keeps gravity's crushing embrace at bay. This period is the star's long, steady life, its enduring phase of stellar existence. However, this stable existence is not eternal. Like all things, it is finite. The star will continue in this state until a critical moment arrives, the point at which the nuclear fusion reaction in its core begins to falter, as it gradually exhausts its primary fuel, the abundant hydrogen. If the star possesses sufficient initial mass, once its hydrogen reserves begin to run low, it will embark on a new, more desperate phase of fusion. The star will begin to combine the newly formed helium into even denser materials. Imagine the core becoming a cosmic forge, steadily building heavier and heavier elements: carbon, then neon, and eventually oxygen and silicon. Each of these subsequent fusion stages provides a temporary reprieve, releasing bursts of energy that allow the star to momentarily resist the inexorable pull of gravity. But each stage is also hotter, more demanding, and ultimately less efficient than the last. Then, the star begins to fuse iron. This marks a catastrophic turning point, a profound shift in the star's destiny. The fundamental issue with iron is that, unlike all the lighter elements that came before it, its fusion into heavier elements does not release any net energy. There is no spare energy to be released, no outward push to be generated. Instead, iron fusion actually consumes energy from the core. It's like trying to fuel a fire by pouring water onto it. The iron simply accumulates in the star's core, growing larger, denser, and utterly inert. There is no longer any energy pushing back against the relentless, overwhelming force of gravity. Very quickly and dramatically, the delicate cosmic scale tips. The outward pressure, once a mighty bulwark against collapse, vanishes. Gravity, unhindered, asserts its absolute dominance. The energy released by this collapse is astounding, truly beyond human comprehension. but its sheer force is entirely dependent on the original monumental mass of the star. It's akin to an immense hammer, forged from pure gravitational power, striking an anvil with an impact of cosmic proportions. The outer layers of the star, still incredibly vast and energetic, rush inwards to meet the rapidly collapsing core. The rebound from that unimaginable blow, the explosive recoil, is what we call a supernova. Matter and energy, in quantities that defy our most vivid imaginings, are blasted out across the universe from this cataclysmic crackback. This is one of the largest, most violent explosions possible in the cosmos. In the intense, fleeting furnace of the supernova, even heavier elements than iron are forged, elements that require such extreme conditions to be created. These include elements all the way up to uranium and beyond, scattering the raw materials for new planets, new stars, and even new life far and wide across the evolving universe. And what remains of the star, this magnificent celestial body that once shone so brightly? Well, the ultimate remnant depends entirely on the initial mass of the star, and thus the sheer, crushing force of that final, devastating blow. If the mass of the star, and consequently the force of the gravitational collapse, was too low to overcome certain fundamental quantum forces, what remains is a neutron star. Imagine this: a tiny, incredibly dense ball of matter, at most only around 25 kilometers in diameter, roughly the size of a small city on Earth. And yet, this minuscule sphere is so densely packed with mass that a single teaspoon of its material would weigh billions of tons. It contains the equivalent mass of 1 million Earths squeezed into a space that could fit within a metropolitan area. The protons and electrons have been crushed together to form a sea of neutrons, creating an object so incredibly dense that it truly defies our intuitive understanding of matter. It is a remarkable, albeit silent, testament to the immense power of gravity. But if the mass of the star, and thus the force of that implacable gravitational blow, was large enough, truly, profoundly, overwhelmingly big, then something even more extreme, something that fundamentally challenges our current understanding, comes into being. At this critical threshold, physics as we know it begins to break down, to unravel at its very seams. And what we are left with, what emerges from such an unthinkable crucible of gravity, is a black hole. It is the ultimate cosmic remnant, a region where the very fabric of existence has been pushed beyond its limits. When you see an image, perhaps a stylized illustration, of a black hole, that dark sphere, that seemingly tangible object, is not actually the black hole itself. Scientists theorize that a black hole's true form is likely even smaller and denser than a neutron star. In fact, it is commonly believed to be infinitely small and infinitely dense, a point known as a singularity. This singularity is not merely a theoretical construct. It is a source of such immense gravitational forces that it warps the very fabric of time and space around it, pulling them into a profound, almost unimaginable curvature. However, the truth is, we don't definitively know what the singularity truly is, or what the absolute interior of a black hole looks like. And the profound reason for this lack of knowledge is something called the event horizon. Let's gently trace the path back through scientific discovery for a moment. We have known since the time of Isaac Newton that all objects with mass exert gravity. It's the force that keeps our feet on the ground and the planets in orbit around the sun. It's a fundamental truth of our universe. However, when Albert Einstein arrived on the scene in 1915 with his revolutionary theory of general relativity, he presented a profoundly new way of understanding gravity. Instead of a force, Einstein described gravity as the curvature of space-time caused by the presence of mass and energy. A brilliant contemporary of Einstein, A physicist named Carl Schwarzschild meticulously reasoned from Einstein's elegant equations that there could indeed exist objects so extraordinarily massive and so incredibly compact that they could create a gravitational pull so overwhelmingly powerful that light itself could not escape their grasp. And if even light, the fastest thing in the universe, a massless photon, could not get out, then absolutely nothing else could escape either. So, when you gaze upon a picture or an artistic rendering of a black hole, you are not actually seeing the black hole itself, not its ultimate, infinitely dense core. What you are truly seeing is the event horizon around it. This is the precise, ethereal demarcation line, the cosmic boundary, where gravity has become so utterly powerful that light, having reached this point, can no longer leave its confines. Beyond this boundary, there is nothing but an impenetrable, eternal darkness, a silence from which no signal can ever return. Its effect on space, on the very geometry of the cosmos, is one thing. But black holes also exert a profound, unsettling impact on another fundamental aspect of the universe-time itself. You see, according to Einstein's revolutionary insights, space and time are not separate entities. They are inseparably connected, interwoven into a single, four-dimensional fabric called space-time. And just as mass warps space, it also warps time. With the singularity's infinitely concentrated point of mass, it stretches and distorts space-time to such an astonishing degree that the event horizon also marks the point where time effectively ceases to exist for an outside observer looking in. Imagine that for a moment. Within the event horizon, space and time, as we intimately understand and experience them, basically cease to have meaning. It becomes a place where there is no where or when in any conventional sense. This profound distortion of time gives rise to a truly fascinating, almost paradoxical phenomenon for an outside observer. If you were watching from a safe distance as matter slowly, inevitably fell into a black hole, your perspective would be extraordinary. As the matter approaches the event horizon, you would witness it slowing down dramatically. It would appear to move in ever-decreasing, agonizingly slow motion until just before it reaches the event horizon. It would seem to stop altogether. You would never, truly never, see it actually cross that cosmic boundary. There would be no satisfying splash, no dramatic absorption. Instead, the matter would simply appear to gradually dim, its light red-shifted into oblivion until you could no longer discern it at all, fading into the perpetual darkness. When these concepts were first theorized back in the early 20th century, astronomers and physicists were deeply uncertain if black holes were anything more than intriguing mathematical curiosities. Were they actually real? It would be nearly 40 years later, in the mid-1960s, that the first tantalizing hints, the very first whispers of evidence for a black hole's existence, began to be recorded. In 1964, utilizing newly developed X-ray satellites, scientists made a curious discovery. They noticed an object in the constellation Cygnus that seemed to be emitting an astonishing amount of X-rays. What truly surprised them, and puzzled them deeply, was that while this object was a powerful X-ray source, scientists could not see the object itself in visible light. If it were a typical star, it ought to emit visible light as well as X-ray radiation. This mysterious invisible X-ray source became known as Cygnus X1. Then, in 1970, as telescope technology advanced further, scientists made another crucial observation. They noticed that whatever Cygnus X1 was, it had formed a binary orbit with a visible, albeit massive, star in its system. This binary dance, this gravitational pairing, allowed scientists to meticulously calculate the mass of the invisible object by observing how the visible star was gravitationally influenced. They discovered, to their astonishment, that this unseen companion was approximately 15 times more massive than our Sun. This was a pivotal moment. Scientists already knew that the densest type of collapsed star, a neutron star, had an upper mass limit of about 3 times the mass of the Sun, an object 15 times the Sun's mass, yet invisible to visible light and emitting prodigious X-rays. Simply could not be a neutron star. It was too heavy. And so, with a growing sense of awe and confirmation, scientists realized that this was, most likely, the first ever discovered black hole. It was a testament to the power of prediction, the triumph of mathematics hinting at realities far stranger than fiction. Since that groundbreaking discovery, we have found many, many more black holes. The most massive ones, the supermassive black holes, seem to reside majestically at the very centers of nearly all large galaxies, including our own Milky Way. We have even, thanks to incredible technological advancements like the Event Horizon Telescope, managed to take what we might call photos of some of them. These images reveal not the black hole itself, but a distinct dark blot, a silhouette, against the swirling, incandescent ring of superheated matter that surrounds them and is inexorably falling into them, their accretion disk. This accretion disk is crucial, for it is how black holes, which by definition cannot emit light themselves, can still be detected through X-rays and other forms of electromagnetic radiation. The intense X-rays and other forms of light that emanate from them actually originate from these accretion disks. In these swirling maelstroms, infalling matter is heated to millions of degrees Celsius due to incredibly intense friction and gravitational compression. This superheated plasma glows brilliantly, revealing the presence of the unseen cosmic devourer at its heart. It is worth noting that black holes with no falling matter, those that are simply drifting in the quiet, empty expanse of space, are virtually invisible. With no bright accretion disk to illuminate their presence, they are truly dark, silent, and incredibly difficult to spot. Their presence is then only detectable through their gravitational influence on nearby stars or gas clouds. Exploring black holes is still a developing, vibrant field in physics and astronomy. There is still so much to learn, so many mysteries yet to unravel about these profound entities. From what we have learned so far, one might wonder, could a black hole ever truly stop being a black hole? Or is its fate to grow forever, consuming matter and radiation until there is nothing left in the universe but itself? It would certainly seem that way, wouldn't it? A relentless, ultimate endpoint. Let your mind gently expand now, like the ripples on a tranquil pond, as we delve deeper into the profound nature of black holes. We have spoken of their birth, from the cataclysmic death of massive stars, and how they warp space-time, creating a boundary beyond which nothing, not even light, can escape. We have touched upon the event horizon, that ethereal sphere of no return, and the mysterious singularity at their heart. But what happens after something crosses that boundary? And is it truly an eternal, one-way journey into oblivion? Imagine, if you will, being an intrepid, albeit fictional, observer bravely nearing the event horizon. From your distant, safe vantage point, you would see time for any object approaching the black hole appear to slow down, stretching out into an eternity. The light from that object would redden, fading, until it seemed to freeze, suspended just at the edge, never truly crossing. This is the phenomenon of gravitational time dilation, a profound consequence of Einstein's theory. Time itself is not absolute. It is relative, deeply intertwined with gravity. Near a massive object, time slows down. Near a black hole, at the event horizon, it appears to stop for an outside observer. But what if you were the object falling in? What would your experience be? This is where the narrative becomes truly mind-bending, almost poetic in its strangeness. From your perspective, Time would continue normally. You would not perceive yourself slowing down or stopping. Instead, you would simply fall, inexorably, towards the singularity. The journey would be swift, perhaps terrifying, perhaps exhilarating, depending on your hypothetical state of mind. However, there's a catch, a rather dramatic one, known as spaghettification. As you approach the black hole, the gravitational pull on your feet, if you were falling feet first, would be significantly stronger than the pull on your head. This difference in gravitational force, known as a tidal force, would stretch you out like spaghetti until your body, or any object, would be torn apart into a stream of individual atoms. This is the ultimate, inescapable fate for anything that ventures too close to a stellar mass black hole. For supermassive black holes, the tidal forces are less extreme at the event horizon, meaning you might cross it intact, only to be spaghettified later as you approach the singularity, but either way, the journey ends in a profound atomic unraveling. And then there is the singularity itself, the point of infinite density, where all the star's mass is compressed into a space smaller than an atom. Our current understanding of physics, particularly general relativity, breaks down at this point. It cannot adequately describe what happens there. This suggests that general relativity, while incredibly successful, is not the complete picture. It needs to be unified with quantum mechanics, the physics of the very small, to truly understand the extreme conditions within a black hole's heart. This quest for a unified theory, a theory of everything, is one of the grandest challenges in modern physics. For many decades, black holes were considered the ultimate cosmic traps, one-way doors from which nothing could ever return. They were seen as eternal devourers, growing larger and larger as they consumed everything in their path. The idea that anything could escape seemed utterly impossible, a violation of their very definition. But then, in the 1970s, a brilliant and visionary physicist named Stephen Hawking proposed a revolutionary idea that challenged this long-held belief. He suggested that black holes are not entirely black, not truly eternal. Instead, they slowly evaporate over incredibly long periods of time, emitting a faint glow of particles. This phenomenon is now known as Hawking radiation. To understand this concept, we need to gently dip our toes into the strange and wonderful world of quantum mechanics. In the quantum realm, the vacuum of space, which we perceive as empty, is actually far from it. It is a bustling, frothing sea of virtual particles constantly popping into existence and then almost immediately annihilating each other. These are particle-antiparticle pairs, for example, an electron and a positron, that spontaneously emerge from nothing, exist for a fleeting moment, and then vanish back into nothingness. They are always born together, and they always annihilate each other. So their existence doesn't violate the laws of energy conservation. It's like a cosmic dance, a constant energetic hum even in the deepest void. Now, imagine this quantum dance happening right at the event horizon of a black hole, sometimes by pure chance. One particle of a virtual pair might pop into existence just inside the event horizon, while its partner pops into existence just outside it. The particle that appears inside the event horizon is trapped. It falls into the black hole, adding a tiny, almost imperceptible amount to its mass. But the particle that appears outside the event horizon is free. It escapes into space, carrying away a tiny bit of energy. Where does this energy come from? It comes from the black hole itself. In essence, the black hole is slowly losing a tiny fraction of its mass energy with each escaping particle. This is Hawking radiation. It is an incredibly faint emission, far too weak to detect from any known black hole today. But theoretically, it means that black holes are not eternal. They are slowly, agonizingly, slowly, radiating away their mass. The rate of Hawking radiation is inversely proportional to the mass of the black hole. This means that smaller black holes radiate more strongly and evaporate much faster than larger ones. A black hole with the mass of our sun would take an unfathomable amount of time to evaporate, far, far longer than the current age of the universe. But a microscopic black hole, perhaps one formed in the early universe, could evaporate in a fraction of a second, releasing a burst of energy equivalent to a small atomic bomb. This concept of Hawking radiation is profound because it suggests a fundamental connection between gravity, quantum mechanics, and thermodynamics, the study of heat and energy. It implies that black holes have a temperature, albeit an incredibly low one, and that they possess entropy, a measure of disorder. This was a groundbreaking insight that opened up entirely new avenues of thought in theoretical physics. It also suggests that information, which was once thought to be irrevocably lost once it crossed the event horizon, might not be entirely gone. This leads to the famous black hole information paradox, a puzzle that continues to challenge physicists today. If a black hole evaporates, what happens to all the information about the matter that fell into it? Is it truly lost forever? Or is it somehow encoded in the Hawking radiation, albeit in a scrambled and unrecognizable form? This remains one of the most hotly debated questions in physics, a testament to the enduring mystery of these cosmic giants. So, black holes are not just cosmic vacuum cleaners, endlessly consuming. They are also, in a deeply subtle way, cosmic radiators, slowly returning energy to the universe. Their existence, their formation, their properties, and their eventual evaporation paint a picture of a universe that is far more dynamic, far more interconnected, and far stranger than we could ever have imagined. They are the ultimate laboratories for extreme physics, places where our understanding of reality is pushed to its very limits. Perhaps, as you gently drift towards sleep, you can imagine a black hole not as a terrifying void, but as a silent, cosmic crucible, a place where the very rules of existence are bent and reshaped, and where the universe whispers its deepest secrets. It is a place of profound transformation, where the familiar gives way to the utterly alien, and where the boundaries of our knowledge are stretched. We have explored the life and death of stars, the birth of these incredible gravitational wells, and the strange phenomena that occur at their edges and within their theoretical hearts. We have touched upon the idea that even these ultimate devourers may eventually fade, leaving behind only the faintest echo of their existence. But what about the space between these cosmic giants, the seemingly empty vastness that separates stars and galaxies? Is it truly empty, a silent canvas upon which the universe paints its grand designs? Or does it hold secrets of its own, a subtle energy, a hidden potential that shapes the very destiny of the cosmos? Let your thoughts unfurl now, like the petals of a night-blooming flower, as we approach the very boundary of understanding when it comes to black holes. We have seen them born from the fiery hearts of collapsing stars, and we have glimpsed the slow, ethereal dance of Hawking radiation, hinting at their eventual distant evaporation. But there is a particular veil, a cosmic curtain, that shrouds the deepest secrets of these gravitational giants, the event horizon. Imagine, if you will, standing at the edge of a great, silent waterfall, not a waterfall of water, but of space itself. Below you, the fabric of space is rushing downwards, faster and faster, drawn into an unseen abyss. The event horizon is precisely this point, the lip of the cosmic waterfall, where the flow of space is so swift, so inexorable, that even light, straining with all its might, can no longer outpace the current. It is the definitive point of no return. This is not a physical wall, not a tangible surface you could touch or feel with your hand. It is an imaginary sphere in space-time, a demarcation line where the escape velocity, the speed you would need to travel to break free from the gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, anything that crosses this boundary is irrevocably bound to the black hole. Its fate is sealed. What is truly remarkable about the event horizon is its subtle, almost deceptive nature. For a distant observer, watching from afar, the approach to this boundary is a spectacle of profound strangeness. As an object, or perhaps even a hypothetical intrepid explorer, draws nearer to the black hole, you would witness a peculiar phenomenon unfold. The object would appear to slow down, as if caught in some invisible cosmic molasses. Its movements would become sluggish, its every gesture agonizingly drawn out. This is the effect of gravitational time dilation, where the intense gravity of the black hole profoundly warps the passage of time itself. Imagine a clock on that approaching object. For you, the distant observer, the ticking of that clock would become slower and slower, each second stretching into minutes, then hours, then days. The light emitted by the object would also be affected, losing energy as it fought its way out of the deep gravitational well. It would shift towards the red end of the spectrum, a phenomenon known as gravitational redshift, until it faded beyond visibility. Its light waves stretched so thin that they disappear. Eventually, from your perspective, the object would seem to freeze just at the event horizon, becoming a ghostly, almost eternal silhouette, gradually dimming until it vanished entirely from your sight. You would never, not truly, witness it cross. It would simply fade, a silent surrender to the invisible. But what about the experience of the object, or the hypothetical explorer, themselves? This is where the story takes on an even more profound layer of contemplation. For the one falling, the experience would be entirely different. As you cross the event horizon, you would feel nothing extraordinary. There would be no sudden jolt, no dramatic barrier, no visible line in the cosmic fabric. You would simply continue to fall, inexorably pulled inward, and your own clock would continue to tick normally. From your perspective, time would flow as it always had. The universe outside, however, would become a blur, compressed and accelerated. You would witness the entire future of the universe unfold in a mere instant behind you, a rapid-fire kaleidoscope of cosmic ages, stars being born and dying, galaxies forming and dissipating, all in the blink of an eye. This is the profound, almost dizzying consequence of relative time. Your perception of time remains consistent, but the universe outside experiences an accelerating rush. And as you fall deeper, beyond the event horizon, you would find yourself in a region where the very concepts of space and time, as we intuitively grasp them, begin to behave in ways that defy our wildest imaginings. Inside the event horizon, space and time effectively trade roles. Where you once moved freely through space, navigating forward and backward, left and right, now movement through space becomes as inevitable as movement forward in time. All paths, all directions, lead irrevocably inward, towards the ultimate, inescapable destination, the singularity. The singularity is the heart of the black hole, the ultimate point of gravitational collapse. Our current scientific understanding paints it as a point of infinite density and zero volume. Every atom, every particle, every ounce of mass that ever fell into the black hole is theorized to be compressed into this single, dimensionless point. It is a concept that utterly challenges our physical intuition, a place where the very laws of physics, the fundamental equations that describe our universe, simply cease to provide meaningful answers. They break down, indicating that our current theories are incomplete at such extreme scales. For the simplest type of black hole, one that does not spin, the singularity is indeed a point, a true dimensionless pinpoint in space-time. Imagine all the mass of a giant star, or even billions of stars, crushed into a space smaller than the head of a pin. Indeed, smaller than any subatomic particle we know. The forces, the energies at play there, are truly beyond comprehension. However, for a spinning black hole, which most black holes in the universe are, the singularity is theorized to be not a point, but a ring. Imagine a tiny, infinitely thin, infinitely dense ring, constantly rotating. This ring singularity arises because the rotational momentum of the collapsing star prevents all its mass from converging to a single point. This theoretical ring is thought to be the heart of a rotating black hole, a place where the fabric of space-time is twisted and torn in an even more complex fashion. The very concept of spin for a point with no volume would be nonsensical. Hence the idea of a ring, or even a more complex structure for a rotating singularity. The implications of such a singularity, whether point or ring, are profound and deeply unsettling for our current physics. Near a ring singularity, for instance, some theoretical models suggest that if one were to follow certain ideal paths, it might become mathematically possible to do truly bizarre things, such as meet up with your own past. This opens the door to time travel paradoxes, concepts that defy our understanding of causality, like the infamous grandfather paradox, the idea of traveling back in time to prevent your own existence. Such paradoxes strongly suggest that our current mathematical models of singularities are not yet complete or entirely accurate. It is a powerful hint that there are deeper, more fundamental laws at play, laws that we have not yet fully uncovered. The reason our current understanding falters so dramatically at the singularity is precisely because it is so incredibly small and dense. To truly explain what goes on inside a black hole, at its ultimate core, we will need a successful merging of two of the most powerful, yet currently incompatible, theories in physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum theory, which describes the behavior of matter and energy at the smallest, subatomic scales. This unified theory, often called quantum gravity, remains the holy grail of theoretical physics, and until it is achieved, the true nature of the singularity, and indeed the deepest secrets of black holes, will remain tantalizingly out of reach, shrouded in cosmic mystery. It may one day turn out that singularities, as we currently envision them, do not exist at all in the hearts of black holes. Perhaps quantum effects at such extreme scales prevent infinite density, smoothing out the fabric of space-time in ways we cannot yet predict. But this is the extent of our knowledge, the frontier of our current understanding, as we peer into the unexplorable heart of these cosmic behemoths. Whatever unimaginable reality lies inside a black hole, beyond the event horizon, and reaching towards the singularity, it is this very core that ultimately powers some of the most extraordinary phenomena in the cosmos. It fuels forces that influence vast swathes of galaxies, and perhaps, one day, it might even offer us keys to unlocking the mysteries of faster-than-light travel or limitless energy. But these are tales for another quiet moment. For now, allow yourself to simply contemplate the event horizon, that silent, invisible curtain where time slows and light surrenders. It is a testament to the immense power of gravity, a cosmic boundary that defines the ultimate prison, yet also sparks our deepest scientific curiosity. It reminds us that our universe holds wonders beyond our immediate grasp, boundaries that humble our understanding, and mysteries that invite us to dream and wonder about the very fabric of existence. As you reflect on this boundary, this point of no return. Consider how such a seemingly simple concept can lead to such profound implications for space, for time, and for the very nature of reality itself. It is a place where intuition fails, and where the universe truly begins to whisper its most arcane secrets. Let your mind unfurl gently now, like a delicate sail catching a cosmic breeze, as we explore another astonishing property of black holes, one that reveals the universe to be even more fluid and dynamic than we might have imagined. We've spoken of gravity as the bending of space-time, a cosmic dimple created by mass. But when a black hole is not merely massive, but also spinning, it adds a layer of complexity and wonder that truly stretches our intuition. Imagine, if you can, a giant, invisible cosmic whirlpool, not a whirlpool of water, but a whirlpool of space-time itself. This is the phenomenon known as frame dragging, a profound prediction of Einstein's general relativity. When a massive object spins, especially something as incredibly dense and energetic as a black hole, it literally drags the very fabric of space-time around it. It's as if the black hole, in its silent, relentless rotation, is stirring the cosmic soup it sits in, pulling everything along for the ride. Think of it like this: if you were standing on a very large, slowly rotating platform, you would feel a gentle pull, a subtle force trying to spin you along with it. But now, imagine that platform is incredibly massive, spinning at an almost inconceivable speed. The pull would become immense, irresistible. This is what happens around a spinning black hole. Space-time itself begins to spin in a vortex, a swirling current that simply cannot be resisted. This cosmic whirlpool creates a distinct region around a spinning black hole known as the ergosphere. The ergosphere is not a solid boundary like the event horizon. It's a zone, a dynamic region of space-time where it is impossible to remain stationary. If you enter the ergosphere, you are caught in the powerful current of frame dragging, and you must move with the rotating space-time. It's like stepping onto a moving walkway that's accelerating faster and faster. You can try to walk against it, but you'll always be carried forward by its inherent motion. The closer you get to the black hole's core within the ergosphere, the faster this frame-dragging effect becomes. At the innermost edge of the ergosphere, the rotation of space-time becomes so intense that it is literally being dragged around at the speed of light. This is a mind-bending concept, not that an object is moving at the speed of light, but that the very space an object occupies is being dragged along at that incredible velocity. From the perspective of a distant observer, anything within this region would appear to be moving at tremendous speeds, even if it were trying to remain still relative to the black hole's center. You might ask, doesn't this violate Einstein's fundamental principle that nothing can travel faster than the speed of light? The answer is nuanced and reveals a fascinating loophole in the cosmic rules. Einstein's law states that nothing can travel faster than the speed of light, locally, that is, within its own immediate frame of reference. If you are in your rocket, you cannot accelerate your rocket beyond the speed of light relative to yourself. But thanks to the profound insights of relativity, it is entirely possible for frames of reference themselves to move relative to each other at astonishing speeds. The space around a spinning black hole provides just such an example. So, while you cannot locally exceed the speed of light in your own tiny patch of space-time, that tiny patch of space-time can itself be moving at speeds that appear superluminal to an outside observer. If you were to somehow sit next to an object within the ergosphere and enter its local frame of reference, it would seem to slow down, once again obeying the familiar laws of physics. It's a truly peculiar effect, a testament to the elegant complexity of space-time. It is precisely by meticulously measuring this frame-dragging effect that scientists can determine the spin of a black hole, a crucial property beyond just its mass and charge. But beyond merely observing this strange dance, there's a truly revolutionary idea proposed by the brilliant mathematician and physicist Roger Penrose. He theorized that there might even be a way to exploit this cosmic whirlpool to extract energy from the very rotation of a black hole. This concept is known as the Penrose process. Imagine, if you will, a hypothetical advanced civilization sending a probe, perhaps even a ship, into the ergosphere of a spinning black hole. The idea is not to fall into the black hole itself, but to utilize the energetic frame-dragging effect. The probe would enter this turbulent region, where space-time itself is being violently spun. Once inside, caught in this immense current, the probe would gain an enormous amount of kinetic energy from the black hole's rotation, speeding up dramatically as it is swept along. The ingenious part comes next. Once it had gained sufficient speed from this cosmic current, the probe would then fire a small portion of its mass, perhaps a detached component or a burst of propellant, in a very specific direction. This ejected mass would be directed in such a way that it falls into the black hole, carrying with it a portion of the negative energy, a concept stemming from the black hole's rotational energy. The remaining larger part of the probe, having shed this small piece of mass, would then be effectively kicked out of the ergosphere, escaping back into normal space. But here's the astonishing part. The part of the probe that escapes would not only regain its original energy, but would also emerge with a net gain of energy extracted directly from the black hole's rotation. The Penrose process, hypothetically, could net you an amount of energy equal to about 20% of the mass of the ejected part of your rocket. Now, 20% might not sound like much at first glance, but remember, according to Einstein's most famous equation, E=mc2, even a tiny amount of mass can be converted into an absolutely colossal amount of energy. Your 20% mass, if fully converted, would produce energy equal to itself multiplied by the speed of light, squared approximately 299,792,458 meters per second, squared. That's an astronomical amount of energy from a relatively small sacrifice of mass. To harness this colossal kinetic energy through the Penrose process, you would, of course, need to travel to the nearest black hole, which is roughly 3,000 light years from us, and you would need a rocket capable of surviving the intense gravitational forces and the chaotic environment within the ergosphere. Ideally, you would want to find a black hole that is not surrounded by a superheated accretion disk, as those disks can reach temperatures of millions of degrees, hot enough to melt and vaporize almost anything into a glowing plasma. So, yes, the practicalities are currently beyond our wildest dreams. However, the implications of the Penrose process and the phenomenon of frame dragging itself are truly revolutionary, hinting at possibilities for faster-than-light travel that defy our conventional understanding. We would not be breaking the speed of light ourselves in our local frame. Instead, we would be convincing the frame of reference we are in to travel at those faster speeds, much like the space-time around a black hole does. It's a subtle but profound distinction, suggesting that the light barrier isn't an absolute wall, but rather a property of local motion. Of course, if this incredible feat requires the energy of a spinning black hole to accomplish, we might be out of luck for practical application for a very, very long time. But it offers an incredible glimpse into what might be possible, a theoretical pathway that challenges our deeply ingrained assumptions about cosmic speed limits. Scientists are already looking into the abstract power of frame dragging for future, highly theoretical concepts of space travel, pushing the boundaries of what we deem achievable. Either way, this all just highlights, once again, how our universe truly is very different from what our everyday experiences and intuitions might lead us to believe. The gentle hum of predictability we feel on Earth fades into a grand symphony of strangeness when we look to the most extreme phenomena the cosmos has to offer. And it leads us to wonder, if black holes can twist and stretch time and space in such incredible ways, what other hidden dynamics are at play in the seemingly empty void between the stars? What subtle energies are constantly being exchanged? What hidden fields are resonating, even in what appears to be nothingness? For the universe is never truly empty. Is it? Allow your mind to settle now, like dust motes gently drifting in a beam of sunlight, as we delve into one of the most astonishing ideas about black holes, an idea that suggests even these ultimate cosmic prisons are not eternal. We've explored how black holes are born from the fiery collapse of stars, how they warp space and time, and how their immense spin can drag the very fabric of reality. But for a long time, the prevailing thought was that once something fell into a black hole, it was gone forever, irrevocably lost to the universe. It seemed that black holes could only grow, silently consuming, until all matter and energy in the cosmos eventually met their end within these dark abysses. However, in 1974, the brilliant physicist Stephen Hawking introduced a groundbreaking concept that painted a profoundly different picture. In his paper, Black Hole Explosions, Hawking postulated that there was, in fact, a subtle way for energy, and therefore mass, to escape a black hole. This revolutionary idea, known as Hawking radiation, suggested that black holes would slowly, agonizingly slowly, release energy over vast stretches of time. And since energy and mass are but two expressions of the same fundamental cosmic coin, as articulated in Einstein's famous EEmc2 equation, this inevitable energy release would result in a gradual reduction in the black hole's mass. Imagine, if you will, a grand cosmic paradox, the ultimate devourer, slowly shrinking, imperceptibly fading. Hawking's calculations showed that as a black hole shrinks, the rate of energy release would subtly speed up, getting faster and faster. This would continue until, in the very last moments of its unimaginably long life, the black hole would release a burst of energy truly gargantuan in its scale, a final, brilliant cosmic sigh, before vanishing entirely from existence. But how could this possibly be true? It is widely understood that an event horizon, that point of no return, is utterly inescapable. How then could any radiation, any energy, ever manage to leave it and eventually cause such a profound black hole explosion? The answer, dear friend, is a strange one, and it relies on some of the most unintuitive ideas of quantum theory, concepts that seem to completely contradict our everyday experience. Yet, if it holds true, then you should be prepared for the universe to be a whole lot stranger, a whole lot more alive in its emptiness than you first thought. To begin to understand Hawking's theory, we need to first gently explore a fundamental idea in quantum physics, the concept of quantum fields. Remember how we considered light moving like a wave, even through a patch of space that appears completely empty. This observation, this persistent movement of energy, hints at a fundamental something that exists even in nothing. Otherwise, if space were truly empty, what exactly would be waving for light to propagate? Scientists call this fundamental, omnipresent fabric of reality a quantum field. In fact, the prevailing belief among quantum physicists is that there are not just one, but several quantum fields, all overlapping each other, all permeating every single patch of the universe, be it past, present, or future. Each quantum field defines a particular type of something. One field might define all the electrons that exist in the universe, while another may define the quarks that make up an atom, where absolutely nothing can be found, where space seems utterly devoid of matter or energy. The quantum field is relatively quiet. Think of it like a perfectly still guitar string that hasn't been strummed, or a graph that simply holds a zero value, a flat, silent line. But wherever in time and space mass or energy can be found. The quantum field at that specific point is resonating. It's humming, vibrating, almost singing. And when the resonance, the vibration, reaches a certain threshold or quantity, the universe expresses that resonance, that vibration, as something tangible, say, an electron or a photon, a tiny packet of light energy. It's profoundly important to note that in this theory, the resonance is not just reacting to a piece of matter, it is the matter. An electron, then, is nothing more than a resonating, vibrating section of the quantum field that specifically defines electrons. This profound truth applies to all energy and all matter. According to Einstein, energy and matter are, after all, simply two sides of the same fundamental coin. In this elegant way, the theory portrays all of the universe you see around you, all its stars and galaxies, all its life and light, as nothing more than an intricate symphony of resonating quantum fields. It's quite a beautiful image, if nothing else, isn't it? The universe as a song being played on an infinite array of invisible strings. But why does this matter so deeply when we talk about black holes? Why is it important to define the universe in this abstract, vibrating way? Well, it all ties into a core idea of quantum physics known as Heisenberg's uncertainty principle. This principle, when applied to the very fabric of quantum fields, introduces a profound element of dynamic unpredictability sometimes. The strings of the universe, even in apparently empty space, simply begin to strum themselves. Without diving too deeply into the intricate mathematical depths of this aspect of quantum physics, imagine this when we are observing objects that are incredibly tiny on the atomic or subatomic scale. It becomes fundamentally impossible to know too much about them simultaneously. For instance, you cannot precisely know both the exact location and the exact direction of travel, or momentum, of an electron at the same instant. This isn't just because our methods of measurement aren't good enough or our instruments aren't precise enough. It's because of some fundamental laws about the nature of the universe itself at its most foundational level. As soon as you try to pinpoint the location of an electron, the very act of trying to measure it disturbs it, causing it to bounce off whatever you are using to observe it, thus making you instantly uncertain of its direction of travel. Conversely, if you know its direction, you cannot know its precise location. Now, apply this profound principle of uncertainty to the silent, vibrating quantum fields that fill all of space. And this is where it gets truly weird. Due to the inherent uncertainties at the quantum level, these quantum fields are constantly fluctuating everywhere. And because of Heisenberg's uncertainty principle, it means that particle and antiparticle pairs can actually pop into and out of existence from the seemingly empty vacuum. The precise how and why gets incredibly complicated, but basically, the universe allows this astonishing phenomenon to occur as long as these virtual particles only exist for an incredibly short period of time, as strictly ruled by these same uncertainty relations. You might be thinking, this can't possibly be a thing. Matter does not just spontaneously pop into existence out of nowhere. Surely, we would have noticed this by now. However, surprisingly, in a famous experiment performed by Hendrik Casimir in the mid-20th century, powerful evidence was found that strongly suggests that this quantum phenomenon might actually be happening all the time. Casimir took two extremely flat, conductive metal plates and placed them incredibly close together in a vacuum, separated by only a minuscule distance. He reasoned that in this tiny gap, only virtual particles of certain sizes and wavelengths could spontaneously pop into existence between them. This effectively limited the number of virtual particles that could appear in the gap. However, on the outside of the plates, All types of virtual particles could pop into existence without restriction. This imbalance, this difference in the quantum fluctuations, theoretically meant that there should be a subtle but persistent difference in pressure exerted on the two sides of each plate. The larger pressure from the greater number of virtual particles on the outside of the plates should subtly push the two plates together. And in the meticulous test, conducted with immense precision, this proved to be precisely the case. The plates were indeed pushed together by a tiny yet measurable force, a strong indication that these quantum fluctuations, these virtual particles, are very much a real aspect of the universe. You might then logically wonder, if particles are constantly appearing out of nowhere, doesn't this defy the sacred laws of conservation of matter and energy? You would be absolutely right to think so. And indeed, to perfectly balance the cosmic scales, whenever a virtual particle appears, a second particle, its antiparticle, also instantaneously pops into existence alongside it. For instance, if an electron, a matter particle, appears, a positron, its antimatter equivalent, also appears. Think of it like a ledger. One is a positive one. The other is a negative one. When added together, they perfectly sum to zero, thus keeping things overall at zero in the cosmic balance. The universe remains perfectly happy, and its fundamental conservation laws are upheld. On top of that, these incredibly short-lived fluctuations in the quantum field quickly crash into each other and annihilate each other, instantly removing both the particle and its antiparticle from existence again. This is why, for the most part, empty space appears to us as simply empty. We don't normally have to worry about them, as their existence is so fleeting, so ephemeral. As a fascinating side note, there is a deep and highly theoretical idea that antimatter is simply matter that is moving in the opposite direction through time. But that, my friend, is a level of weirdness that we don't need to get into here. A thought for another quiet, contemplative journey. The important part for our current discussion is that the quantum fields are constantly resonating, constantly fluctuating, and constantly canceling each other out. This intricate, self-canceling dance is precisely why, for the most part, empty space seems to remain empty and peaceful to our senses. However, what would happen? What profound change would occur if you could somehow stop only some of those fields from resonating? What if the delicate balance of creation and annihilation, this constant quantum hum, was somehow disturbed? And that, dear listener, is precisely where black holes enter our story once more. Black holes, in a profound and subtle way, act a bit like putting your thumb on the guitar string of the universe. Due to the extreme curvature of space-time around their event horizons, certain resonances in the quantum fields are subtly dampened down, while others are not. The perfect instant creation and annihilation of virtual pairs can be disrupted. Hawking, in his brilliant leap of intuition, imagined sketching a line through time in a patch of space where a black hole was born. He envisioned a quantum field that resonated along this line, stretching from before the existence of the black hole into the deep future after it formed. Before the birth of a black hole, all is normal, all is in balance. Quantum fields are all resonating freely, their virtual particles and antiparticles appearing and perfectly canceling each other out, preserving the cosmic zero. However, the dramatic emergence of the black hole's event horizon fundamentally changed the curvature of space around it, and crucially, outside it. Hawking realized, as he looked at the intricate mathematics, that certain pulses, certain specific types of quantum fluctuations, were now missing their perfect opposite numbers. The profound gravitational distortion had, in effect, created a subtle imbalance in the quantum vacuum near the event horizon. Not everything was being canceled out perfectly anymore. Indeed, outside the event horizon, traveling away from the black hole, he found theoretical resonances that perfectly matched the shape of thermal radiation, a faint, outward-flowing energy. This radiation, now known as Hawking radiation, is energy, and energy, fundamentally, cannot simply form from nothing without a cosmic cost. Therefore, as the black hole was theoretically creating this radiation, the black hole itself would have to pay the price. Every tiny piece of Hawking radiation that escaped into the cosmos would thus coincide with an equal, almost imperceptible amount of energy and mass lost from the black hole. This constant, minuscule drain would, over an unimaginably vast amount of time, slowly reduce the black hole down to nothing, causing it to evaporate entirely. If it truly exists, Hawking radiation is a phenomenon that is almost like money spontaneously appearing outside of a bank, while simultaneously an equal amount of money vanishes from the vault inside that very same bank. It's a subtle, constant draining of the black hole's very essence. It is also, unfortunately, incredibly difficult to prove definitively through direct observation. Hawking predicted that this radiation would be extraordinarily cold, far, far colder than the cosmic microwave background radiation that fills the entire universe. Furthermore, its wavelength, the size of its energy waves, would be incredibly long as the black hole's event horizon itself, given that some black holes have event horizons the size of entire solar systems. We currently have absolutely no way of detecting this incredibly faint, incredibly long wavelength radiation. We would only really begin to detect it once the universe itself had gone cold and dead, when there was nothing else around to interfere or mask its faint signal, a time when we, as a species, would probably not be around anymore to do the detecting. However, in spite of the formidable observational challenges, the intricate mathematics behind Hawking radiation seems to be remarkably sound and consistent with our current understanding of physics. And remarkably, scientists have recently taken tantalizing steps towards indirectly proving its existence in the laboratory. In Technion, the Israel Institute of Technology, researchers embarked on an ingenious idea to circumvent the immense difficulty of measuring a real-life black hole. They did this by creating an analog, a simplified model that would mimic the properties of a black hole in a more accessible medium, a sonic black hole. This experiment relied on a crucial fact: sound moves much, much slower than light. This makes it far easier to create a medium that moves faster than sound. When such a medium moves faster than the speed of sound, any sound waves traveling in the same direction can never quite escape it, effectively creating a sonic event horizon. Intriguingly, Hawking's original mathematics, which described the properties of gravitational black holes, worked perfectly well for these sonic black holes too. And so, theoretically, Hawking radiation ought to be detectable from it. After repeating the experiment an astonishing 97,000 times over 124 days of continuous, meticulous experimentation, the researchers detected multiple instances of sonic Hawking radiation. And critically, it matched Hawking's precise predictions for how his radiation might behave. While this groundbreaking laboratory experiment does not definitively prove that Hawking radiation is real for actual cosmic black holes, the fact that Hawking's elegant math worked so beautifully and consistently for this sonic analog is a strong and compelling implication that he might indeed be onto something profound. It whispers to us that Hawking radiation might just be real, a subtle cosmic hum emanating from the darkest corners of the universe. So, if you were to hypothetically fall into a black hole, could you ever escape? Probably not in any conventional sense. However, if you waited until almost the very end of the universe, until countless eons had passed, The black hole might just radiate away all its mass through Hawking radiation until the mass and energy that once made up your existence was completely removed from inside the event horizon. Would that truly count as escaping? It's probably not a very appealing thought for a journey back home, is it? Probably best just not to go in at all. This deep dive into Hawking radiation not only challenges our understanding of black holes, but also opens up profound questions about the very nature of reality, about what nothing truly means, and about the interconnectedness of gravity and the quantum world. It shows us that even the most seemingly stable and eternal objects in the universe might have a lifespan, a quiet end written into the fundamental laws of physics. Allow your awareness to gently expand now, like a slow breath filling a vast, quiet space, as we move beyond the immediate vicinity of black holes and consider the seemingly empty canvas upon which the cosmos paints its grand designs. We have spoken of the profound density of black holes, their ability to warp time and space, and even their theoretical evaporation. But what about the vast stretches between these cosmic behemoths, the seemingly silent, desolate voids that separate stars, galaxies, and clusters of galaxies? Is this truly nothingness, an inert backdrop against which the drama of the universe unfolds? Or does it hold secrets of its own, a subtle energy, a hidden potential that shapes the very destiny of the cosmos? For centuries, even millennia, the concept of empty space was precisely that, empty. A vacuum, a void, a region devoid of matter, energy, or even light. It was the absence of everything. And in our everyday experience, this intuition holds true. If you remove all the air from a container, you create a vacuum, and it feels like nothing is left. But as we have learned, especially when delving into the quantum realm, the universe is far more intricate, far more alive than our immediate senses can perceive. The vacuum of space, it turns out, is anything but empty. In fact, it is teeming with activity, a subtle, dynamic hum that influences everything. This brings us to a concept that is both deeply mysterious and profoundly influential: dark energy. Imagine, if you will, the universe not as a static, unchanging arena, but as a living, breathing entity. For a long time, after the initial burst of the Big Bang, scientists believed that the expansion of the universe, the outward rush of galaxies moving away from each other, would gradually slow down. This was a logical assumption. Gravity, after all, is a force of attraction. Every galaxy, every star, every particle of matter in the universe exerts a gravitational pull on every other particle. So, it stood to reason that this universal gravitational attraction, acting like a cosmic brake, would inevitably cause the expansion to decelerate, perhaps even leading to an eventual big crunch where the universe would collapse back in on itself. For decades, astronomers meticulously observed distant supernovae exploding stars that act as standard candles, because their intrinsic brightness allows us to calculate their distance from us. By measuring how bright they appeared and how much their light had been stretched, red-shifted by the expansion of the universe, scientists could infer how fast the universe was expanding at different points in its history. The expectation was to see evidence of this deceleration. Then, in the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, made a truly astonishing discovery. Their observations of these distant supernovae revealed something utterly unexpected. The expansion of the universe was not slowing down. On the contrary, it was accelerating. The galaxies were not only moving away from each other, but they were doing so at an ever-increasing rate. This was a bombshell. It was as if you threw a ball into the air, expecting it to slow down as gravity pulled it back, but instead, it suddenly started speeding up, rushing away into the sky. This acceleration implied the existence of a mysterious, unseen force, something that was actively pushing the universe apart, overcoming the collective gravitational pull of all the matter within it. This enigmatic force was given the name dark energy. What is dark energy? This is where the gentle whispers of science meet the profound silence of the unknown. The truth is, we don't know. It remains one of the greatest unsolved mysteries in cosmology. However, scientists have several leading hypotheses, each as fascinating and mind-bending as the last. One of the leading candidates for dark energy is the cosmological constant, a concept first introduced by Albert Einstein himself. When Einstein was developing his theory of general relativity, his equations initially predicted a dynamic, expanding or contracting universe. At the time, the prevailing scientific view was that the universe was static, unchanging. To reconcile his equations with this belief, Einstein reluctantly added a term to his equations, the cosmological constant, which represented a repulsive force inherent to space itself, a force that would counteract gravity and keep the universe from collapsing. Later, when Edwin Hubble's observations definitively proved that the universe was indeed expanding, Einstein famously called the cosmological constant his biggest blunder. However, with the discovery of accelerating expansion, the cosmological constant has made a dramatic comeback. Perhaps it wasn't a blunder after all, but a profound, albeit premature, intuition. In this view, dark energy is an intrinsic property of space itself. It's not something that sits in space. It is space. As space expands, more space is created, and therefore, more dark energy comes into existence, leading to an ever-increasing repulsive force. It's like a cosmic feedback loop. Expansion creates more dark energy, which causes more expansion. This idea suggests that the vacuum of space, far from being empty, possesses a fundamental inherent energy density that exerts a negative pressure, pushing things apart. Another fascinating hypothesis is that dark energy is a new, exotic type of energy field that permeates all of space, similar to other fundamental fields we know, but with very peculiar properties. This hypothetical field is sometimes called quintessence. Unlike the cosmological constant, which is constant, quintessence would be a dynamic field, meaning its strength and density could change over time and space. This would allow for a more complex evolution of the universe's expansion, perhaps explaining subtle variations in the acceleration over cosmic history. Imagine a subtle, invisible ocean of energy, constantly shifting and flowing, subtly influencing the very fabric of reality. A third, even more radical idea suggests that dark energy isn't a new form of energy at all, but rather a manifestation of modifications to gravity itself on very large scales. Perhaps Einstein's theory of general relativity, while incredibly accurate on solar system and galactic scales, needs to be subtly tweaked when applied to the entire universe. This would imply that our understanding of gravity, while profound, is not yet complete, and that there are deeper, more intricate rules governing the cosmos at its grandest dimensions. The implications of dark energy are truly monumental. It currently makes up about 68% of the total energy density of the universe. Think about that for a moment. All the visible matter stars, galaxies, planets, us makes up only about 5% of the universe. The mysterious dark matter, which we'll explore in another quiet moment, accounts for about 27%. This means that the vast majority of our universe, nearly 7/10 of everything that exists, is composed of something we cannot see, cannot touch, and do not yet understand. It is a silent, invisible force that dictates the ultimate fate of the cosmos. If dark energy continues to dominate, and the acceleration of the universe's expansion continues indefinitely, the future of the cosmos could be a lonely one. Galaxies would continue to recede from each other at an ever-increasing pace, eventually moving so far apart that their light would never reach each other. The night sky, once ablaze with billions of galaxies, would become an empty, silent canvas. Stars would eventually burn out, black holes would evaporate, and the universe would end in a cold, dark, infinitely dilute state, a scenario sometimes referred to as the Big Freeze or the heat death of the universe. It is a chilling, yet profoundly quiet, vision of the ultimate cosmic end. However, the nature of dark energy is still very much an open question. Its properties could change over time. What if quintessence, for example, were to weaken or even strengthen in the distant future? What if it were to become even more powerful, leading to a scenario known as the Big Rip, where the accelerating expansion becomes so extreme that it eventually tears apart galaxies, stars, planets, and even atoms themselves? Or what if it were to somehow reverse, causing the universe to eventually collapse back in on itself in a big crunch? These are profound questions, and the answers lie hidden within the very nature of this enigmatic force. The study of dark energy is at the forefront of modern cosmology. Scientists are building new, more powerful telescopes, launching sophisticated satellites, and designing ingenious experiments to try and unravel its secrets. They are meticulously mapping the distribution of galaxies across vast cosmic distances, studying the subtle patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, and observing the evolution of galaxy clusters. Each piece of data, each new observation, is a tiny whisper from the universe, offering clues about the true nature of this mysterious force that governs its expansion. Perhaps, as you drift into a peaceful slumber, you can imagine dark energy not as a terrifying, unknown force, but as the universe's own subtle breath, expanding, stretching, and shaping the very fabric of existence. It is a reminder that even in the seemingly empty spaces, there is a profound, active presence, a silent energy that orchestrates the grand cosmic dance. It is a testament to the fact that our universe is still full of profound mysteries, inviting us to wonder, to explore, and to embrace the vastness of what we do not yet know. The universe, in its quiet, expansive grandeur, is not just made of the stars and galaxies we can see. It is woven from threads of invisibility, from the subtle hum of quantum fields, and from the enigmatic push of dark energy. And just as we ponder the unseen forces that shape the cosmos, we might also consider the unseen matter that holds galaxies together, the silent, gravitational glue that binds the visible universe. What is this invisible scaffolding, this cosmic ghost that exerts such a powerful influence? Allow your mind to settle now, like dust motes gently drifting in a beam of sunlight, as we delve into one of the most astonishing ideas about black holes, an idea that suggests even these ultimate cosmic prisons are not eternal. We've spoken of their birth from the fiery collapse of stars, how they warp space and time, and how their immense spin can drag the very fabric of reality. But for a long time, the prevailing thought was that once something fell into a black hole, it was gone forever, irrevocably lost to the universe. It seemed that black holes could only grow, silently consuming, until all matter and energy in the cosmos eventually met their end within these dark abysses. However, in 1974, the brilliant physicist Stephen Hawking introduced a groundbreaking concept that painted a profoundly different picture. In his paper, black hole explosions. Hawking postulated that there was, in fact, a subtle way for energy, and therefore mass, to escape a black hole. This revolutionary idea, known as Hawking radiation, suggested that black holes would agonizingly slowly, release energy over vast stretches of time. And since energy and mass are but two expressions of the same fundamental cosmic coin, as articulated in Einstein's famous EMMC2 equation, this inevitable energy release would result in a gradual reduction in the black hole's mass. Imagine, if you will, a grand cosmic paradox, the ultimate devourer, slowly shrinking, imperceptibly fading. Hawking's calculations showed that as a black hole shrinks, the rate of energy release would subtly speed up, getting faster and faster. This would continue until, in the very last moments of its unimaginably long life, the black hole would release a burst of energy truly gargantuan in its scale, a final, brilliant cosmic sigh, before vanishing entirely from existence. But how could this possibly be true? It is widely understood that an event horizon, that point of no return, is utterly inescapable. How then could any radiation, any energy, ever manage to leave it and eventually cause such a profound black hole explosion? The answer, dear friend, is a strange one, and it relies on some of the most unintuitive ideas of quantum theory, concepts that seem to completely contradict our everyday experience. Yet, if it holds true, then you should be prepared for the universe to be a whole lot stranger, a whole lot more alive in its emptiness than you first thought. To begin to understand Hawking's theory, we need to first gently explore a fundamental idea in quantum physics, the concept of quantum fields. Remember how we considered light moving like a wave, even through a patch of space that appears completely empty. This observation, this persistent movement of energy, hints at a fundamental something that exists even in nothing. Otherwise, if space were truly empty, what exactly would be waving for light to propagate? Scientists call this fundamental, omnipresent fabric of reality a quantum field. In fact, the prevailing belief among quantum physicists is that there are not just one, but several quantum fields, all overlapping each other, all permeating every single patch of the universe, be it past, present, or future. Each quantum field defines a particular type of something. One field might define all the electrons that exist in the universe, while another may define the quarks that make up an atom. Where absolutely nothing can be found, where space seems utterly devoid of matter or energy, the quantum field is relatively quiet. Think of it like a perfectly still guitar string that hasn't been strummed, or a graph that simply holds a zero value, a flat, silent line. But wherever in time and space mass or energy can be found, the quantum field at that specific point is resonating, it's humming, vibrating, almost singing. And when the resonance, the vibration, reaches a certain threshold or quantity, the universe expresses that resonance, that vibration, as something tangible, say, an electron or a photon, a tiny packet of light energy. It's profoundly important to note that in this theory, the resonance is not just reacting to a piece of matter, it is the matter. An electron, then, is nothing more than a resonating, vibrating section of the quantum field that specifically defines electrons. This profound truth applies to all energy and all matter. According to Einstein, energy and matter are, after all, simply two sides of the same fundamental coin. In this elegant way, the theory portrays all of the universe you see around you, all its stars and galaxies, all its life and light, as nothing more than an intricate symphony of resonating quantum fields. It's quite a beautiful image. If nothing else, isn't it the universe as a song being played on an infinite array of invisible strings? But why does this matter so deeply when we talk about black holes? Why is it important to define the universe in this abstract, vibrating way? Well, it all ties into a core idea of quantum physics known as Heisenberg's uncertainty principle. This principle, when applied to the very fabric of quantum fields, introduces a profound element of dynamic unpredictability sometimes. The strings of the universe, even in apparently empty space, simply begin to strum themselves. Without diving too deeply into the intricate mathematical depths of this aspect of quantum physics, imagine this when we are observing objects that are incredibly tiny. On the atomic or subatomic scale, it becomes fundamentally impossible to know too much about them simultaneously. For instance, you cannot precisely know both the exact location and the exact direction of travel, or momentum, of an electron at the same instant. This isn't just because our methods of measurement aren't good enough, or our instruments aren't precise enough. It's because of some fundamental laws about the nature of the universe itself at its most foundational level. As soon as you try to pinpoint the location of an electron, the very act of trying to measure it disturbs it, causing it to bounce off whatever you are using to observe it, thus making you instantly uncertain of its direction of travel. Conversely, if you know its direction, you cannot know its precise location. Now, apply this profound principle of uncertainty to the silent, vibrating quantum fields that fill all of space. And this is where it gets truly weird. Due to the inherent uncertainties at the quantum level, these quantum fields are constantly fluctuating everywhere. And because of Heisenberg's uncertainty principle, it means that particle and antiparticle pairs can actually pop into and out of existence from the seemingly empty vacuum. The precise how and why gets incredibly complicated, but basically, the universe allows this astonishing phenomenon to occur as long as these virtual particles only exist for an incredibly short period of time, as strictly ruled by these same uncertainty relations. You might be thinking, this can't possibly be a thing. Matter does not just spontaneously pop into existence out of nowhere. Surely, we would have noticed this by now. However, surprisingly, in a famous experiment performed by Hendrik Casimir in the mid-20th century, powerful evidence was found that strongly suggests that this quantum phenomenon might actually be happening all the time. Casimir took two extremely flat, conductive metal plates and placed them incredibly close together in a vacuum, separated by only a minuscule distance. He reasoned that in this tiny gap, only virtual particles of certain sizes and wavelengths could spontaneously pop into existence between them. This effectively limited the number of virtual particles that could appear in the gap. However, on the outside of the plates, all types of virtual particles could pop into existence without restriction. This imbalance, this difference in the quantum fluctuations, theoretically meant that there should be a subtle but persistent difference in pressure exerted on the two sides of each plate. The larger pressure from the greater number of virtual particles on the outside of the plates should subtly push the two plates together. And in the meticulous test, conducted with immense precision, this proved to be precisely the case. The plates were indeed pushed together by a tiny yet measurable force, a strong indication that these quantum fluctuations, these virtual particles, are very much a real aspect of the universe. You might then logically wonder, if particles are constantly appearing out of nowhere, doesn't this defy the sacred laws of conservation of matter and energy? You would be absolutely right to think so. And indeed, to perfectly balance the cosmic scales, whenever a virtual particle appears, a second particle, its antiparticle, also instantaneously pops into existence alongside it. For instance, if an electron, a matter particle, appears, a positron, its antimatter equivalent, also appears. Think of it like a ledger. One is a positive one, the other is a negative one. When added together, they perfectly sum to zero, thus keeping things overall at zero in the cosmic balance. The universe remains perfectly happy. and its fundamental conservation laws are upheld. On top of that, these incredibly short-lived fluctuations in the quantum field quickly crash into each other and annihilate each other, instantly removing both the particle and its antiparticle from existence again. This is why, for the most part, empty space appears to us as simply empty. We don't normally have to worry about them, as their existence is so fleeting, so ephemeral. As a fascinating side note, there is a deep and highly theoretical idea that antimatter is simply matter that is moving in the opposite direction through time. But that, my friend, is a level of weirdness that we don't need to get into here. A thought for another quiet, contemplative journey. The important part for our current discussion is that the quantum fields are constantly resonating, constantly fluctuating, and constantly canceling each other out. This intricate, self-canceling dance is precisely why, for the most part, empty space seems to remain empty and peaceful to our senses. However, what would happen? What profound change would occur if you could somehow stop only some of those fields from resonating? What if the delicate balance of creation and annihilation, this constant quantum hum, was somehow disturbed? And that, dear listener, is precisely where black holes enter our story once more. Black holes, in a profound and subtle way, act a bit like putting your thumb on the guitar string of the universe due to the extreme curvature of space-time around their event horizons. Certain resonances in the quantum fields are subtly dampened down, while others are not. The perfect instant creation and annihilation of virtual pairs can be disrupted. Hawking, in his brilliant leap of intuition, imagined sketching a line through time in a patch of space where a black hole was born. He envisioned a quantum field that resonated along this line, stretching from before the existence of the black hole into the deep future after it formed. Before the birth of a black hole, all is normal, all is in balance. Quantum fields are all resonating freely, their virtual particles and antiparticles appearing and perfectly canceling each other out, preserving the cosmic zero. However, the dramatic emergence of the black hole's event horizon fundamentally changed the curvature of space around it, and crucially, outside it. Hawking realized, as he looked at the intricate mathematics, that certain pulses, certain specific types of quantum fluctuations, were now missing their perfect opposite numbers. The profound gravitational distortion had, in effect, created a subtle imbalance in the quantum vacuum near the event horizon. Not everything was being canceled out perfectly anymore. Indeed, outside the event horizon, traveling away from the black hole, he found theoretical resonances that perfectly matched the shape of thermal radiation, a faint, outward-flowing energy. This radiation, now known as Hawking radiation, is energy, and energy, fundamentally, cannot simply form from nothing without a cosmic cost. Therefore, as the black hole was theoretically creating this radiation, the black hole itself would have to pay the price. Every tiny piece of Hawking radiation that escaped into the cosmos would thus coincide with an equal, almost imperceptible amount of energy and mass lost from the black hole. This constant, minuscule drain would, over an unimaginably vast amount of time, slowly reduce the black hole down to nothing, causing it to evaporate entirely. If it truly exists, Hawking radiation is a phenomenon that is almost like money spontaneously appearing outside of a bank, while simultaneously an equal amount of money vanishes from the vault inside that very same bank. It's a subtle, constant draining of the black hole's very essence. It is also, unfortunately, incredibly difficult to prove definitively through direct observation. Hawking predicted that this radiation would be extraordinarily cold, far, far colder than the cosmic microwave background radiation that fills the entire universe. Furthermore, its wavelength, the size of its energy waves, would be incredibly long as the black hole's event horizon itself. Given that some black holes have event horizons the size of entire solar systems, we currently have absolutely no way of detecting this incredibly faint, incredibly long wavelength radiation. We would only really begin to detect it once the universe itself had gone cold and dead, when there was nothing else around to interfere or mask its faint signal, a time when we, as a species, would probably not be around anymore to do the detecting. However, in spite of the formidable observational challenges, the intricate mathematics behind Hawking radiation seems to be remarkably sound and consistent with our current understanding of physics. And remarkably, scientists have recently taken tantalizing steps towards indirectly proving its existence in the laboratory. In Technion, the Israel Institute of Technology, researchers embarked on an ingenious idea to circumvent the immense difficulty of measuring a real-life black hole. They did this by creating an analog, a simplified model that would mimic the properties of a black hole in a more accessible medium, a sonic black hole. This experiment relied on a crucial fact: sound moves much slower than light. This makes it far easier to create a medium that moves faster than sound. When such a medium moves faster than the speed of sound, any sound waves traveling in the same direction can never quite escape it, effectively creating a sonic event horizon. Intriguingly, Hawking's original mathematics, which described the properties of gravitational black holes, worked perfectly well for these sonic black holes too. And so, theoretically, Hawking radiation ought to be detectable from it. After repeating the experiment an astonishing 97,000 times over 124 days of continuous, meticulous experimentation, the researchers detected multiple instances of sonic Hawking radiation, and critically, it matched Hawking's precise predictions for how his radiation might behave. While this groundbreaking laboratory experiment does not definitively prove that Hawking radiation is real for actual cosmic black holes, the fact that Hawking's elegant math worked so beautifully and consistently for this sonic analog is a strong and compelling implication that he might indeed be onto something profound. It whispers to us that Hawking radiation might just be real, a subtle cosmic hum emanating from the darkest corners of the universe. So, if you were to hypothetically fall into a black hole, could you ever escape? Probably not. Not in any conventional sense. However, if you waited until almost the very end of the universe, until countless eons had passed, the black hole might just radiate away all its mass through Hawking radiation, until the mass and energy that once made up your existence was completely removed from inside the event horizon. Would that truly count as escaping? It's probably not a very appealing thought for a journey back home. Is it probably best just not to go in at all? This deep dive into Hawking radiation not only challenges our understanding of black holes, but also opens up profound questions about the very nature of reality, about what nothing truly means, and about the interconnectedness of gravity and the quantum world. It shows us that even the most seemingly stable and eternal objects in the universe might have a lifespan, a quiet end written into the fundamental laws of physics. Allow your thoughts to expand gently now, like a deep, slow breath, filling the quiet spaces within you, as we turn our attention to the sheer scale of black holes across the cosmic tapestry. We have contemplated their mysterious formation, their profound warping of space-time, and even the subtle, ethereal whisper of their eventual evaporation. Now, let us consider their size, from the unimaginably tiny to the truly gargantuan, and the enigmatic story of how they grow, whispering secrets from the very dawn of time. Black holes, as we've noted, come in an astonishing variety of dimensions, a cosmic spectrum of gravitational might. The smallest observed black holes, sometimes referred to as micro black holes, are truly remarkable in their compactness. Imagine a mass comparable to that of our Earth's moon, approximately 7.35 × 10^22 kilograms, compressed into a space no larger than 0.2 millimeters in diameter. To put that into perspective, that's thinner than a human hair, yet packing the entire mass of our moon. This incredibly high density truly gives you a sense of the immense compression at play within a black hole. These micro black holes are mostly theoretical, or could have formed in the extreme conditions of the early universe, but they highlight the incredible density that defines these objects. Moving up the scale, we encounter stellar black holes. These are the remnants of the massive stars we discussed earlier, the ones whose violent deaths leave behind a gravitational singularity. Stellar black holes typically possess a mass roughly 10 times that of our Sun, yet they are contained within a diameter of only about 60 kilometers. Imagine our familiar Sun, condensed into a sphere no wider than a bustling city. The density remains mind-boggling, a testament to the immense power of gravity that has crushed stellar material into such an incredibly compact form. These are the more common black holes scattered throughout galaxies, including our own. Beyond stellar black holes, there is a fascinating, still somewhat mysterious category known as intermediate black holes. These possess masses that are truly astounding, reaching up to 1,000 times the mass of our Sun. All of this colossal mass is squeezed into a diameter of around 2,000 kilometers, which, while substantial, is still much smaller than the Earth itself. The existence of these intermediate black holes has been harder to confirm, but evidence is steadily mounting that they form a crucial link between the stellar mass black holes and the true titans of the cosmos. They might be found in the centers of dense star clusters, acting as gravitational anchors for these stellar groupings. But it is the largest black holes that truly dwarf us, both in mass and in their profound influence on the cosmic landscape. These are the supermassive black holes, or SMBHs, and they reside majestically at the very centers of nearly all large galaxies. Their masses range from a staggering 100,000 times to an unimaginable 10 billion times the mass of our Sun. To give you a sense of their sheer scale, their event horizons can span enormous distances, from 0.01 astronomical units up to an incredible 400 astronomical units. An astronomical unit, you might recall, is the average distance from the Earth to the Sun. So, a supermassive black hole could comfortably swallow our entire solar system many times over within its event horizon. Imagine a region of absolute darkness that stretches beyond the orbit of Neptune, encompassing worlds and light within its silent grasp. These supermassive black holes have been in existence since almost the very start of the universe, and their story is one of continuous, relentless growth. They have been accumulating more and more matter, silently absorbing gas, dust, stars, and even other black holes, continually increasing their already gargantuan mass over billions of years. They are the gravitational anchors, the silent giants that sit at the cosmic heart of their galaxies, their immense gravity influencing the very structure and dynamics of their galactic homes. What is truly astonishing, and perhaps a little counterintuitive, is that some of the most massive black holes we currently know of are actually among the youngest in terms of cosmic age. When we gaze upon distant galaxies through our powerful telescopes, we are not just looking across vast stretches of space. We are also looking back in time. The light from these faraway galaxies has traveled for billions of years to reach our instruments, meaning we are observing them as they were billions of years ago, when the universe was much younger. For example, If we observe a galaxy 10 billion light-years away, we are seeing it as it existed 10 billion years ago, when the universe itself was only a few billion years old. So, if the universe is approximately 13.8 billion years old, and light from a distant galaxy has taken, say, 10 billion years to reach us, then the galaxy we are observing can only be, at most, around 3.8 billion years old from our perspective. This is incredibly young for a galaxy. Yet, within these youthful, distant galaxies, we often find the most massive, supermassive black holes. This seems to present a paradox, doesn't it? Surely closer, and thus older. Supermassive black holes should be more massive, having had so much more extra time to consume infalling matter. So, what cosmic forces are at play here? Consider TON 618, one of the very largest supermassive black holes we know of. It boasts an incredible mass of 66 billion solar masses. By itself, its mass is comparable to that of an entire large galaxy like our own Milky Way. However, TON 618 is exceptionally far away from us, and the light emitted by it has taken a staggering 10.8 billion years to reach our telescopes. This means we are observing it as it was 10.8 billion years ago. This implies that the black hole itself could be at most around 2.8 billion years old at the time we are observing it. By comparison, our own Milky Way galaxy is approximately 13.6 billion years old, yet the supermassive black hole found at our galaxy's core, Sagittarius A, is only about 4 million solar masses. And the Andromeda galaxy's supermassive black hole, while larger than ours, is still only around 200 million solar masses. One of the significant factors to consider here is the inherent difficulty in detecting and measuring black holes. This is still a relatively new and rapidly developing field of research. Our technology has only truly allowed us to begin directly observing black holes, or more accurately, the regions around them, in the last few decades. Even with cutting-edge instruments like the Event Horizon Telescope, imaging even a single black hole takes an immense amount of time and complex data processing. Thus, our general understanding of the vast population and distribution of black holes across the cosmos is still quite limited, a mere whisper in the vastness. In fact, most of the incredibly distant and massive black holes we know about can only be seen because they are quasars. TON 618 is a prime example of a quasar. A quasar forms when matter is pouring into a black hole's accretion disk at a truly incredible rate. Because of this phenomenal influx of material, the accretion disk erupts into a quasar, shining with an almost incomprehensible brilliance. Quasars can only be sustained as long as vast amounts of matter are continuously falling into them. Otherwise, they quietly revert back to being dark, mostly unobservable black holes. It is challenging to fully grasp the intricate physics of the accretion disk in such extreme conditions, but it is widely believed that the friction and gravitational compression within these disks are so immense that the accretion disk of a quasar by itself can produce thousands of times more light than entire galaxies combined. TON 618, for instance, produces as much light as an astonishing 140 trillion suns. This colossal luminosity completely outshines the galaxy it resides in, to the point that we cannot even discern the host galaxy from our distant perspective. The quasar's intense glare renders it invisible. However, precisely because quasars are the brightest objects in the universe, they can be seen from truly astronomical distances. This leads to a crucial point known as Malmquist bias. This bias refers to a phenomenon where brighter objects, even when further away, appear more plentiful in our observations. In reality, we simply cannot see the dimmer objects like non-quasar black holes or ordinary galaxies at those extreme distances. This implies that the largest supermassive black holes might actually be distributed fairly evenly throughout the universe, but we can only detect the ones that are currently in their brilliantly active, quasar phase when they are billions of light years away. If a galaxy has a very large black hole, but it's not a quasar because it's not actively feeding, we won't see it beyond a certain distance, because the galaxy itself is much, much dimmer than a quasar. Another profound reason why we don't observe the absolute biggest black holes as frequently in our immediate cosmic neighborhood or in the older parts of the universe closer to us is directly related to the nature and evolution of the universe itself. Shortly after the Big Bang, during the early universe, matter was far more densely packed together. The cosmos was a much more chaotic, gas-rich environment. Because of this abundance of available gas and dust, quasars were far more common back then. They needed extreme amounts of matter falling into them to give off light, and there was simply a lot more loose gas available to fuel these magnificent cosmic engines during the early stages of the universe. Not only has the universe expanded dramatically since then, diluting the matter density, but over cosmic time, a significant portion of that available gas has been converted into stars. Many of the largest types of stars eventually end their lives by turning into neutron stars and black holes themselves. This means that this gas is no longer readily available to be recycled back into the interstellar medium to feed supermassive black holes. Less available gas in the cosmic environment naturally means less gas will fall into a supermassive black hole, slowing its growth rate. One of the prevailing theories for the ultimate fate of the universe is actually based on this very process, a scenario sometimes called the Big Freeze or heat death, where, after some trillions of years, all the gas in the universe is eventually converted into stars or locked away in stellar remnants like black holes and neutron stars. Even now, we observe some galaxies, known as elliptical galaxies, where their gas has been almost completely used up, meaning no new stars can form within them. These galaxies appear smooth and featureless, devoid of the active star-forming regions found in spiral galaxies. In contrast, spiral galaxies like our Milky Way still retain significant gas and dust structures, and thus can still produce new stars, though at a slower rate than in the early universe. It is interesting to note that most of the largest, most active supermassive black holes, the quasars we observe from the early universe, appear to be located in what would later evolve into large elliptical galaxies. In these systems, the gas had already lost much of its angular momentum and fallen efficiently into the galaxy's central supermassive black hole, fueling its rapid growth. With spiral galaxies, this process of gas accretion hasn't happened to the same extent, or perhaps occurred more slowly over time. One such trigger for gas losing its angular momentum and spiraling into the galactic center could be the immense gravitational influence of nearby galaxies, or even catastrophic collisions with other galaxies. Such mergers would funnel vast amounts of gas and dust towards the galactic core, igniting a quasar phase. In addition to the decreasing density of gas due to cosmic expansion and star formation, the universe as a whole is becoming less chaotic and more spread out. The era of frequent galaxy mergers and abundant cold gas clouds has largely passed. This means that the number of active quasars has significantly decreased over cosmic time. And so, the only quasars we still observe, some of which are the largest black holes we know of, are the ones that were active a very long time ago, their light only now reaching us across the vast distances of space. This might be why there is currently no active quasar within 500 million light-years of us, a testament to the universe's aging and quieting. So, why do the largest supermassive black holes often appear to be the youngest? Well, although it may appear that way due to our observational limitations, it might not actually be the fundamental truth at all. We can simply measure incredibly distant, incredibly bright quasars because their overwhelming luminosity allows their light to travel across cosmic eons and still be detected. older and closer black holes may also be immensely large, perhaps even larger in some cases. But because of Malmquist bias, and because they are no longer in an active, blazing quasar phase, we simply haven't found them yet, or cannot measure their full extent as easily. As studies continue, as our telescopes become more powerful and sophisticated, and as our understanding of cosmic evolution deepens, we will undoubtedly start to get a far more complete and nuanced picture of the universe around us, revealing perhaps even grander giants hidden in the quiet darkness. Let your mind float softly now, like a feather drifting on a warm, unseen current, as we step into a realm of cosmic speculation, a mirror image of the profound gravitational behemoths we have explored. We have journeyed through the dark, inescapable embrace of black holes, those regions where space and time warp to an extreme. But in the grand tapestry of space-time, as described by Einstein's elegant equations, black holes are not the only way the universe can show off its magnificent, dramatic curves. In theory, there exist equally curved, yet diametrically opposite, regions of space-time called white holes. They earn their name, white holes, precisely because in many fundamental ways, they are the exact opposite of black holes. If a black hole is a cosmic drain, relentlessly pulling everything inward, a white hole, in contrast, would be a cosmic fountain, an unceasing emitter, from which light and matter could burst forth, but into which nothing could ever fall. Imagine the relentless absorption of a black hole reversed. Instead of a one-way street inwards, it is a one-way street outwards. To truly appreciate this peculiar concept, let us begin with a simple analogy, allowing our thoughts to be gentle and playful. If I were to ask you to imagine a cone, your mind would likely conjure one of two familiar shapes, either something that points upwards, like a brightly colored traffic cone standing on a road, or something that points downwards, like a delightful ice cream cone waiting to be filled. These are the cones we encounter in our everyday, tangible world. However, if you were to write down the most general mathematical equation for a cone and then attempt to graph it, you would discover something quite different. The pure mathematical cone looks like two cones glued together at their very tips, one pointing upwards and one pointing downwards. What we perceive as cones in the real world are, in fact, merely chopped up pieces, incomplete fragments of this full, elegant mathematical form. And this, dear friend, is precisely how black holes are in the realm of theoretical physics. Let me explain. Many of the black holes we observe in the sprawling cosmos are the dramatic remnants of massive stars, whose extreme gravitational forces cause them to collapse inward upon themselves. Once such a black hole is created, it becomes permanently separated from the surrounding universe by that familiar spherical barrier, the event horizon. As we've explored, anything can fall into the black hole, but nothing, not even the fleetest ray of light, can ever escape. This intricate structure of space-time around a forming black hole can be neatly summarized in what physicists call a Penrose diagram. This is a clever way of representing an infinite expanse of space-time within a finite, manageable drawing. The key feature of a Penrose diagram is that light rays, traveling at the ultimate speed limit, always move upwards at precise 45-degree angles. This simple rule makes it elegantly clear to distinguish between regions where light can or cannot enter or exit. In such a diagram, typically, there's a region 1, which represents our regular familiar universe, encompassing the original star before its collapse and everything outside the black hole, stretching from the infinite past to the infinite future. Then, there's a region 2, which is the black hole itself. In this diagram, you can visually trace how light, and indeed ordinary matter which moves slower than light at angles steeper than 45 degrees, can easily enter the black hole's region 2. However, Once inside, all paths inevitably lead to the singularity, and it becomes utterly impossible for light to exit. But while this particular diagram beautifully represents the kind of black hole we are used to observing in the real world, the one born from a collapsing star with a finite past, it is, crucially, only one piece of the full mathematical description of black holes and general relativity. In other words, this familiar real-world black hole is merely the lone ice cream cone of black hole diagrams. It is an incomplete, truncated view of the full mathematical solution. So, what happens if we let go of the constraints of the real world for a moment and imagine an ideal black hole, one with an infinite past? What if we set aside the baggage of collapsing stars and all the other intricate details of the physical universe? What then would be the black hole, analog of the full, complete mathematical cone? It might look like a simple, elegant extension of our original Penrose diagram, but this more complete diagram comes with a profound twist, a physics that is, in a sense, upside down. Region 1 would still represent our familiar, regular universe, and Region 2 would still be our black hole, with its inevitable singularity in its future, the point of no return for anything falling in. But the comprehensive mathematics of this idealized solution also describes something else entirely, something that looks remarkably like the inverse of a black hole. This is Region 3. Instead of having a singularity in its future, this Region 3 has a singularity in its past, and if you carefully draw the motion of light rays within this region, still at their characteristic 45-degree angles, you would clearly see that it is straightforward, indeed natural, for light to leave Region 3 to burst forth from it. However, it is fundamentally impossible for light, or anything else, to enter it. This type of region, this cosmic fountain, is precisely what we would call a white hole. It is the space-time analog of our upward-pointing traffic cone. But the story doesn't end there. If you look even further in this expanded mathematical diagram, beyond the white hole, you might discern a patch of space-time labeled Region 4. This region possesses the same fundamental connections to the black and white holes in the middle, but it exists as a completely separate, parallel universe. It is entirely disconnected from the universe we started in, Region 1. In this theoretical construct, it is impossible for even light, traveling at its ultimate speed, to traverse from Region 1 to Region 4. They exist as distinct, yet mathematically linked realities. The profound upshot of all this elegant mathematics is that the same fundamental mathematical equations describing our regular universe and a black hole also, quite naturally, describe a parallel universe and a white hole. This does not automatically mean that every black hole we observe in the cosmos comes neatly attached to a white hole, or indeed to a parallel universe. Just as with our cones, the real, physical universe can, and likely does, contain only chopped up pieces, specific fragments of the full mathematical solution. However, what it does mean is that even if white holes are demonstrably less common than their black hole counterparts, or even if there aren't any white holes connected to our observable universe at all, existing perhaps as isolated theoretical curiosities, it doesn't make their concept any less scientific. In a profound sense, they are equally consistent with the fundamental laws of physics as articulated by general relativity. To return to our analogy, if you were to imagine that ice cream cones remained immensely popular and ubiquitous in the world, while traffic cones, for whatever reason, became incredibly difficult to produce and were gradually phased out of existence, that wouldn't make the fundamental idea or mathematical possibility of a traffic cone any less real or valid. This, more or less, encapsulates the current status of white holes in theoretical physics today. The notion of a white hole as a direct mathematical consequence of Einstein's equations makes perfect sense. It's a beautiful, elegant solution, but its physical realization, its actual presence in our universe, remains elusive. It's entirely possible that any white holes that might have existed in the tumultuous early universe were inherently unstable. Perhaps they quickly collapsed or diffused, or were somehow phased out of existence by the chaotic conditions of the cosmic dawn. They might be mathematically elegant, but physically improbable. If you are wondering, however, whether there could be some more stable white holes out there, perhaps incredibly tiny ones, that have simply escaped our current observational capabilities, you are certainly not alone in that thought. This is a fascinating line of inquiry that continues to intrigue physicists, and you should definitely continue to gently wonder, for we will touch upon the tiniest possible white holes and how they might relate to the ultimate fate of black holes in just a few more quiet moments together. But first, I want to ensure we're not leaving any threads dangling. We promise not only white holes, but also wormholes, those fantastical tunnels through space-time that could connect parallel universes or distant points in our own. So, prepare yourself to float a little deeper, as we are about to journey to a whole new level of warped space-time, where the very fabric of reality twists in ways that defy easy description. Let your thoughts gently unravel now, like fine threads from a spool, as we prepare to weave through one of the most fantastical and mind-bending concepts that emerge from the equations of space-time wormholes. We have drifted through the profound darkness of black holes and even glimpsed the theoretical light of white holes, their cosmic counterparts. Now, let us consider the possibility of bridges between these extremes, tunnels through the very fabric of reality that could, in theory, connect distant points in our universe or even lead to entirely separate, parallel realms. For many, the idea of traveling through a wormhole evokes images from science fiction, a shimmering portal, a shortcut across impossible distances. And indeed, for a long time, the notion felt like nothing more than a fanciful invention of storytellers. After all, even though these regions are mathematically possible in theory, there has been absolutely no direct evidence that wormholes actually exist in our universe. But remember, a mere 100 years ago, black holes themselves were purely theoretical constructs, elegant solutions on paper, dismissed by many as mere mathematical curiosities. And now, we believe there are literally billions of them out there, waiting for our telescopes to reveal their secrets. So, let us hold on to that sense of wonder, that gentle openness as we explore these ethereal threads through reality. We begin by returning to a fundamental truth about black holes, one that we explored earlier, the no-hair theorem. This elegant principle states that, once formed, a black hole is remarkably simple. It sheds almost all information about the star it came from, behaving as if it were bald, devoid of any distinguishing features beyond a very few intrinsic properties. Specifically, a black hole can have only 3 intrinsic properties that we can measure: mass, charge, and angular momentum, or spin. The Penrose diagram we use to illustrate the simple, non-spinning black hole, the ice cream cone analogy, with its single event horizon and an unavoidable singularity, represented the most basic kind of black hole, one that is electrically neutral and completely stationary. But the diagrams, and indeed the physics, for black holes that possess charge, or more commonly, spin, are far more complex. And crucially, they are also far more exciting, for they completely alter our understanding of singularities and give rise to new, profoundly fascinating regions of space-time. These are the realms where wormholes could, in theory, exist. Let us now focus on the Penrose diagram for a spinning black hole. The complexities multiply beautifully here. Instead of just four distinct regions of space-time, as in the non-spinning case, there are now typically 8 types of regions that repeat themselves in an infinite pattern of interconnected universes. Regions 1 through 4 are familiar to us. Region 1, our regular universe. Region 2, the black hole itself. Region 3, the theoretical white hole. And Region 4, the parallel universe entirely disconnected from Region 1. But now that the black hole is spinning, its internal geometry changes in a profound way. The singularity itself is no longer an unavoidable point in its future. And similarly, the white hole no longer has an unavoidable singularity existing in its past. The immense rotation subtly alters the space-time curvature near the very center. So, what theoretically happens after you cross the event horizon of a spinning black hole? At first, you would be drawn towards the center of the black hole, just as you'd expect, inexorably pulled inward by the immense gravitational current. However, you would eventually cross a second, crucial threshold. This is known as the inner horizon, or sometimes the Cauchy horizon. Beyond this inner boundary, the geometry of space-time begins to un-W-warp in a truly astonishing way, theoretically allowing you to stop yourself from falling even deeper inward. In these innermost regions, marked perhaps as regions 5 and 7 on a more complex diagram, you could, in theory, float freely towards or even away from the center of the black hole. You could even, if you dared, theoretically touch the singularity itself, which, for a spinning black hole, takes the shape of a ring, not a point, as we briefly touched upon. Though, as we discussed, I certainly wouldn't recommend it, as our physics still breaks down at such extremes. Here, in these innermost regions of a highly curved, rapidly rotating space-time, you are, theoretically, officially in a wormhole. This exotic tunnel, known in this context as an Einstein-Rosen bridge, is a theoretical passage through space-time itself. If it weren't for the fact that you would be permanently separated from everyone who stayed in your original universe, Region 1, this would certainly have been the perfect moment for you to brag about your wild space-time adventures, a tale of cosmic journeys unparalleled. At this profound juncture, deep within the wormhole, you would also be faced with a bit of a fork in the road, a choice of cosmic paths. One theoretical option is to keep moving inward, perhaps even attempting to go around the ring singularity itself. This path, according to some models, could theoretically take you to regions like 6 or 8 in the diagram, leading to even more mind-bending possibilities, including those pesky causal paradoxes where you might interact with your own past. However, it's quite possible that the existence of such a path is actually a flaw in the current predictions of general relativity when pushed to these extremes, rather than a true description of reality, precisely because going even a single loop around the singularity could lead to such disturbing time travel paradoxes, like the classic grandfather paradox. Such issues often hint that our theories need refinement. A safer, and perhaps more commonly envisioned, theoretical bet would be to turn around and move outwards, crossing back into the inner horizon that you just came out of. This path, if traversable, would theoretically take you into Region 3, a white hole. This white hole would then, in its nature, as a cosmic fountain, gently carry you all the way out to a brand new universe, a realm similar in structure to the one you started out in originally. But, alas, without your friends or family waiting for you. In fact, by the time you arrived in this new cosmos, your old universe would have already experienced an infinite amount of time. You would truly be living in a whole new definition of the future, a cosmic traveler across eons. Now, let us gently step back into the more grounded realm of our current understanding. as profoundly fun and tantalizing as that theoretical journey through the wormhole sounds. The harsh realities of physics suggest that you probably couldn't survive it in practice. The immense gravitational and tidal forces near the inner horizon would likely be far too extreme for any biological entity, or even the sturdiest spacecraft, to withstand. Furthermore, there's a very good chance, perhaps even a certainty, that the wormhole itself would be inherently unstable. The moment you, or even a tiny particle of matter, disturbed its delicate space-time geometry by attempting to traverse it, the wormhole would likely collapse, pinching off and preventing any passage. It's like trying to cross a bridge made of soap bubbles. The slightest touch might pop it. So, how much of this intricate mathematical structure can we truly expect to see realized in the raw, physical world? Spinning black holes, complete with their event horizons and frame-dragging ergospheres, appear to be ubiquitous across the universe. They are very much a real and observed phenomenon. However, what goes on inside of them beyond that event horizon remains largely unknown and highly theoretical. There are two main reasons why the physics inside real black holes might be fundamentally different from what these idealized Penrose diagrams would lead you to believe. First, when black holes form from the turbulent, chaotic collapse of massive stars, some of the pristine assumptions that go into making these elegant Penrose diagrams are inevitably violated. The diagrams often assume perfect symmetry, or that the black hole has existed forever in a perfectly empty universe. Real black holes are born from violent processes and are constantly interacting with their environment, perhaps even swallowing random, infalling humans or stray particles. This messy reality likely alters the internal geometry in ways our current simplified models don't fully capture. Second, and perhaps more importantly, the very theory of general relativity that is used to construct these Penrose diagrams might itself only be approximately correct. It is incredibly successful in describing gravity on large scales, but it is known to break down near the singularity, where the curvature of space-time becomes most extreme. This breakdown strongly suggests that general relativity is not the ultimate, complete theory of gravity. It needs to be supplanted or augmented by a theory of quantum gravity, which would describe the behavior of space-time at the quantum level. Until we have a robust theory of quantum gravity, there's a good chance that some of the more problematic predictions of the diagrams, especially those involving naked singularities or time travel paradoxes, are not true features of a highly curved space-time, but rather artifacts of an incomplete theory. However, the theoretical existence of white holes themselves, as mathematically consistent counterparts to black holes, remains more of an open possibility, leaving plenty of room for gentle speculation about how they might come to be, and whether they might leave any subtle observational footprints for us to discover. One fascinating hypothesis that has recently gained some quiet traction is that a white hole is not some separate cosmic entity from the Big Bang, but rather is born whenever a black hole dies. And no, this isn't some magical story of cosmic reincarnation or voodoo. It's a genuine attempt, rooted in theoretical physics, to understand the full life cycle of black holes, with at least some level of mathematical backing. You see, even an isolated black hole in an otherwise empty space will not remain perfectly static forever. As we discussed, it will continuously emit particles known as Hawking radiation, causing it to gradually shrink and lose mass over an unimaginably vast amount of time. But what happens once the black hole reaches an incredibly tiny mass, often referred to as the Planck mass, just about 20 micrograms, an almost imperceptible speck? This is where our current theories hit a wall. We have no way of precisely predicting what future awaits it at such an ultra-microscopic scale, at least not without a full working theory of quantum gravity. This is where fascinating approaches like loop quantum gravity step in, Loop quantum gravity is a proposed link between general relativity and quantum mechanics, a theory in which space itself is not a smooth, continuous fabric, but rather is made up of discrete, tiny loops. In short, the equations of loop quantum gravity predict that instead of continuing to shrink even smaller than the Planck mass, a tiny black hole is instead more likely to quantum tunnel into a white hole. Imagine a profound quantum leap, a shift in its very nature. This newly formed white hole would then begin to slowly, gently spew out its contents back into the universe over an extended period of time. Incredibly, even though this newly formed white hole would be similarly small and light, the internal geometry of the original black hole could have been stretched into a thin tube with an extremely large volume before its quantum transition. This store of internal structure and information, this vast amount of entropy, could potentially open a pathway for any information that originally fell into the black hole to be eventually recovered in the distant, distant future, albeit in a scrambled or diffused form. This would elegantly provide a theoretical resolution to the decades-long puzzle in theoretical physics known as the information paradox, the question of whether information is truly lost forever inside a black hole. As the white hole gently releases this information, this faint diffused echo of what once was, it would begin to slowly fade out of existence. The space-time around it would gradually lose its extreme curvature, and its long, quiet life cycle would finally come to a close. But before this journey ends, allow me to leave you with one last profound thought, a whisper from the very edges of cosmic understanding. In general relativity, our entire universe is predicted to have had a singularity in its past, namely, some 14 billion years ago, at the moment of the Big Bang. In this profound way, our universe, in its initial explosive expansion, is like an uncharged, stationary white hole, something from which everything bursts forth and into which nothing can fall. But if loop quantum gravity suggests that white holes can be born when black holes collapse, could the same be true about the creation of our entire universe? Could it be that our grand, expanding universe was not born from an absolute nothingness, but rather from the ashes, the ultimate collapse, of an older, contracting space-time, a universe that came before, as crazy, as mind-bending as this seems? Loop quantum gravity offers intriguing theoretical pathways that suggest this might very well be the case. However, there are so many different, beautiful ideas for how such a cosmic transition could have happened, so many nuanced theoretical possibilities that we would need an entirely new, quiet journey, a whole new video, just to begin to scratch the surface. So, if you ever find yourself wondering, if you feel a gentle curiosity about how the Big Bang could have actually been a big bounce, a cosmic rebound from a previous existence, let that thought gently carry you into your peaceful rest. The history of the universe may hold more surprises, more profound and beautiful twists than we can currently imagine. Let your thoughts gently linger now in the quiet space we have created as we embark upon the final stretch of our cosmic journey. We have traversed the profound depths of black holes, glimpsed the ethereal nature of white holes, and even pondered the theoretical pathways of wormholes. Our exploration has consistently revealed that the universe, at its most fundamental level, is far stranger and more wondrous than our everyday intuition can grasp. It has been a journey through the bending and twisting of space-time, a quiet contemplation of what is possible, even if not yet fully observed. And now, we reach the very edge of current scientific thought, touching upon ideas that whisper about the ultimate fate of black holes and, perhaps, the very beginning of our own universe. We left our last conversation with a tantalizing thought, the possibility that a white hole could be born from the death of a black hole, a cosmic metamorphosis. This idea, which sounds almost like a magical story of reincarnation, is a genuine attempt to understand the complete life cycle of black holes, rooted deeply in the principles of a revolutionary theoretical framework called loop quantum gravity. Recall that when a black hole emits Hawking radiation, it slowly, over an unimaginable expanse of time, shrinks and loses its mass. But what truly happens when a black hole becomes incredibly tiny, reaching the elusive Planck mass a mere 20 micrograms, an almost imperceptible speck? At this extreme, our cherished theory of general relativity, so elegant and successful on grand scales, breaks down completely. It can no longer provide meaningful answers. This is a profound signal that we need a more complete, more encompassing theory, one that unifies the macro world of gravity with the micro world of quantum mechanics. This is the realm of quantum gravity. Loop quantum gravity offers one of the leading, most compelling attempts at such a unification. In this profound theoretical framework, space itself is not a smooth, continuous fabric, as we instinctively perceive it. Instead, it is hypothesized to be made up of discrete, incredibly tiny, interconnected loops, much like an intricate, shimmering network or a fine, almost invisible weave. Imagine the very fabric of reality as a vast, granular tapestry woven from these fundamental loops. Within this framework, the singularity, that point of infinite density at the heart of a black hole where general relativity falters, is not allowed to form. The quantum nature of space prevents infinite compression. Instead, the equations of loop quantum gravity predict that as a black hole shrinks to the Planck mass, instead of continuing to crush itself into nothingness, it undergoes a profound quantum transition. It is more likely to quantum tunnel into a white hole. Imagine, if you can, a truly cosmic leap, a fundamental shift in its very identity. The black hole, having consumed and compressed matter for eons, reaches its ultimate quantum limit. Instead of simply vanishing, the compressed information and energy, instead of becoming infinitely dense, are subtly rebounded or bounced outwards. This newly formed white hole would then begin to slowly, gently, spew out its contents back into the universe over an extended, though still vast period of time. This is not a violent explosion in our human timescale, but a gentle, drawn-out emission, an unspooling of cosmic information. Incredibly, even though this newly formed white hole would be infinitesimally small in light, the internal geometry of the original black hole could have been stretched into a vast, thin tube with an extremely large volume before its quantum transition. This stored information, this immense amount of entropy, a measure of the internal disorder and complexity, could potentially provide a pathway for any information that originally fell into the black hole to be eventually recovered in the distant future. This theoretical resolution elegantly offers a potential solution to one of the most stubborn and deeply debated puzzles in theoretical physics, the black hole information paradox. This paradox asks whether information, the fundamental quantum properties of particles that fall into a black hole, is truly lost forever once it crosses the event horizon. If information is indeed lost, it would violate a fundamental principle of quantum mechanics. Loop quantum gravity's quantum bounce, or tunneling mechanism, provides a tantalizing possibility. The information is not truly destroyed, but is instead processed and then released from the resulting white hole, albeit in a scrambled or diffused form that might be incredibly difficult to decode. It's like taking a book, shredding it, and then meticulously reconstructing it from the tiny pieces that slowly emerge from a cosmic machine. The information is there, but its retrieval is a monumental task. As this theoretical white hole gently releases this information, this faint, diffused echo of what once was, it would begin to slowly fade out of existence, losing its mass and energy. The space-time around it would gradually lose its extreme curvature, and its long, quiet life cycle would finally come to a close. It is a profound vision of cosmic recycling, where even the ultimate devourers have an ultimate end, a return to the broader universe. But this captivating idea extends even further, touching upon the very grandest question of all, the origin of our own universe. In the classical theory of general relativity, our entire universe is predicted to have had a singularity in its past, namely, approximately 13.8 billion years ago, at the moment of the Big Bang. This singularity represents the point of infinite density from which all of space-time and matter expanded. In this profound way, our universe, in its initial explosive burst, is conceptually like an uncharged, stationary white hole, something from which everything bursts forth, and into which nothing can fall. But if loop quantum gravity suggests that white holes can be born when black holes collapse and then bounce into a new existence, could the same principle apply to the birth of our entire universe? Could it be that our grand expanding universe, with all its stars, galaxies, and quiet spaces, was not born from an absolute nothingness, but rather from the ashes, the ultimate extreme collapse of an older, previous universe that contracted until it reached a quantum boundary? Could the Big Bang that gave birth to our cosmos actually have been a big bounce, a cosmic rebound from a previous existence, a profound act of cosmic recycling on the largest possible scale? As mind-bending, as profoundly counterintuitive as this seems, loop quantum gravity offers intriguing theoretical pathways that suggest this might very well be the case. Instead of a singular, inexplicable point of creation, the Big Bang could be seen as a turning point, a bridge from a contracting phase of a prior universe to the expanding phase we observe today. It replaces the enigmatic singularity with a smooth, continuous quantum transition, a bounce that avoids the mathematical breakdown. However, it is crucial to remember that these are deeply theoretical waters, ideas whispered at the very frontier of our knowledge. There are so many different, beautiful, and complex ideas for how such a cosmic transition could have happened. So many nuanced theoretical possibilities that we would need an entirely new, quiet journey, a whole new contemplation, just to begin to scratch the surface. But the very possibility, the gentle suggestion from the mathematics of loop quantum gravity, allows us to dream of a universe that is endlessly cyclical, eternally transforming, a grand dance of cosmic birth, death, and rebirth. This journey through black holes, white holes, and the quantum fabric of reality has brought us to the edge of what is known and into the vast expanse of what is yet to be discovered. It reminds us that our universe is a place of endless wonder, a canvas for profound mysteries that invite us to keep asking questions, to keep exploring, and to keep embracing the beautiful uncertainty of existence. As you drift now, let these thoughts become like distant stars, twinkling gently in the vast quiet of your mind. There is no need for answers, only the peace of wonder itself. Allow the vastness of the cosmos to cradle your thoughts, to soothe your spirit. Feel the gentle rhythmic hum of existence, the silent dance of unseen forces that weave the tapestry of all that is. May this journey through the grandest questions bring you a deep sense of calm, a tranquil stillness, as you surrender to the quiet wisdom of the universe. This content is for informational and entertainment purposes only, and is not intended to be a substitute for professional medical advice, diagnosis, or treatment. Always seek the advice of your physician or other qualified health provider with any questions you may have regarding a medical condition.